the solution to enzyme-related problems are actually pretty straightforward. And the reason for that is because these types of solutions that are needed to rid people of age-related lipofuscin and enzyme degradation problems are already in clinical use. They're in clinical use for things that are called lysosome storage diseases. And again, how I mentioned before when we were talking about solutions to mitochondrial DNA problems, where since aging is not classified as a treatable disease, what we have to do is look to other branches of medicine where we have the same interests. We're interested in solving the same kind of problem but for different purposes. Lysosome storage diseases is one of those things. Like in trying to find out solutions for mitochondrial problems with proteins there, what we're going to do is look at people who have inherited genetic problems for lysosomes. So essentially what happens to these people is that they're missing a particular enzyme that is used normally in bodily functions, and that causes big problems because these are more problems than the age-related problems, because the reason the body has designed these enzymes in the first place is because that particular kind of junk builds up very quickly. That's why an enzyme was developed for it. And whereas these age-related problems in the brain and heart of undegradable material, those took a long time to build up, past the normal lifespan of a person when it was evolving to its environment. So these are very serious issues. And as I said, they are already in use in the clinic. People who have these diseases, they can go and get treated for it, and this is called enzyme replacement therapy, where basically what they do is they get injections of this either mutated enzyme or missing enzyme, and it replaces it. And here is the basic approach to solving one of these enzyme-related problems. First, people need to identify the enzyme they need. If it's a lysosome storage disease, they need to find out which enzyme is missing or not working properly. For aging, what they'll need to do is find an enzyme to break down that particular type of junk. And we'll come back to this again later. We're going to look at what is in clinics right now first. Second is to get the enzyme into the appropriate cell. Different cells build up junk at different rates. So for something like Gaucher's disease, they have an inability to break down certain fats. So these fats build up in the places where fats are metabolized, in the liver and different organs like this. Also in white blood cells as well. Next is to get the enzyme, once it's in the cell, into the lysosome. Otherwise, it doesn't work just floating around inside of just the intracellular space. It has to be in the enzyme because it needs that high acid environment in order to work. And plus, if we just had some enzyme floating around in the cell, it's just going to start reacting with everything, and that will do more damage rather than good. And fourth is the immune system response. People's immune systems learn to recognize self from non-self when they are developing in the womb. There are these progenitor immune cells. Regardless, that's not really important, but the whole point is that since these enzymes were not with people since birth, the immune system could possibly recognize it as foreign and attack it. Luckily, so far in these treatments, this hasn't been a problem, even though this enzyme replacement therapy is for something that people normally have already, but since it wasn't with them since birth, their immune system recognizes it as foreign. And people have not really had much of an immune system reaction to it. It's been very mild, if any at all. So that's good news. But for related to aging, I can see a way around this. So let's go on the internet. So here's an article on just the history of enzyme replacement therapy. If people are interested, it just kind of goes from back in the 70s, basically, where this all started, the idea came from. And just different, the first one, and they have a whole host of enzyme replacement therapies. It's not just one. I'm using this one, Gaucher's disease, because it's the most common one. This is the one that they developed first, because it's the one that most people have. And again, it's characterized by an inability to degrade certain types of lipids. The enzyme normally does this. Since the enzyme is not functioning properly, this stuff builds up very quickly, and we can see some pictures here of people who have it. So you can see this kid right here, his liver and other internal organs are very swollen because it's not able to break down this fat. So here you can see as well. And you don't see any adults on here because they are, as we said, normally it takes them a while to identify this disease, unless we already know that the parents have it, because it's a genetic disorder, but often they don't know they have it. So it takes, normally by the time they're a small child, you can obviously tell something is wrong with a kid like this. But there aren't any adults on here because we have a treatment for it now, that's why. So basically this whole idea was just to present that the way to solve other enzyme problems for our purposes related to aging, different junk in the brain, heart, in the arteries, this same approach can be used, identifying the enzyme. Now we're looking for enzymes. So firstly, we're looking for enzymes that have never been made by the human body. But there are plenty of places to find enzymes. And a book I read a while ago it was pretty funny. Lipofuscin, when certain wavelengths of light are shined on it, it glows red. And it was funny. It was asking a question, why? Because they were looking for the same answer of how do we fix this problem. They say, why don't graveyards glow with this light? And that's because there are bacteria in the soil that break all of this stuff down. Bacteria have enzymes, or certain strains of bacteria have enzymes that get rid of this. That's why it hasn't been building up in the ground for years and years of people dying, mass graves, things like this. We don't see anything there, any remains after a while. That's because bacteria have this enzyme. So what the idea is, and this idea has been used in multiple different fields, from cleaning up oil to all kinds of things. It's just finding the bacteria with the proper enzyme, finding out what that enzyme is. Now we have the code for that enzyme. So that's not a big deal. Second is to get the enzyme into the cell. Depending on what cell it is, we will have to code differently for that. If it's going to the liver, it has a certain code. If it's going to the brain, that has a certain code. If it's going to heart, that has a certain code. And this has been a problem for even the treatments that are in the clinic right now, because some of these enzyme-related disease, it causes these things to build up in their brain as well. But so far in the clinics, they have not been able to get these enzymes that they're injecting to cross the blood-brain barrier. And that is a problem. That means we cannot treat anything that happens in the brain. There are certain molecules that can cross the blood-brain barrier, but it's very difficult to cross. A lot of people are working on it right now, so this is something that people are still actively trying to get around, just for the treatment of these diseases as well. But I have a different idea, which I'll talk about later when we get to the immune response. Thirdly, getting the enzyme into the lysosome. As I said, it does no good in the main body of the cell. It may actually do harm if it is activated, but fortunately, since most of these enzymes need high acid environments in order to work, they won't work if it's not acidic enough. So that's not really a problem if it didn't get into the enzyme, but we need it to get into the enzyme in order for it to work. And they've accomplished this in several different ways. One way is just to put stuff on the molecule to make the lysosome think that it's actually junk that it needs to degrade. So it just takes this in, and then once it's in, it's in. Now it'll be working in there. And fourth is the immune response. Again, since we're going to be introducing things into the body that we weren't born with, the body doesn't recognize it as self, there could potentially be a immune reaction. So far in people it hasn't been very strong at all. It's been very mild or not there. But hypothetically, if there was, well, let me talk about that later. Let me talk about just other ideas people have as well of addressing this. So firstly, what they're doing right now is just injecting the enzymes and then having different sequences to take it to this appropriate cell and then into the lysosome. But other people have presented ideas as well. Another idea is to introduce bone marrow that's been genetically modified to produce this enzyme. That way it gets around the immune response and you have a constant supply of this enzyme being released and then being uptaken by the cells. And that's one thing. Another is very similar to what we did with the mitochondrial DNA. It's just to do some gene splicing. Just put this gene into the nuclear DNA and then it builds it in the main body of the cell and takes it into the lysosome. I haven't really seen so much of this related to aging, but I had a different idea personally. I don't really see the need to do gene splicing or to introduce bone marrow. I think the injections, unless there's some particular reason why it wouldn't work well for that particular enzyme, I see no reason why the injection shouldn't be the best one. Here's my reasoning. For these diseases, Gaucher's disease, for example, the injections need to be done every 2 weeks. And this is because these types of junk accumulate very quickly. It's very common. That's why the body has developed enzymes against it, because it's something that accumulates very quickly. And we would die very rapidly if we didn't break this stuff down. As far as aging is concerned, though, the whole point the body didn't build enzymes for this, because it takes so long for it to accumulate. It didn't see it necessary, because you were going to be killed by something else before this became a serious problem. So it takes 20, 30, 40, 50 years plus for this to build up into an amount where it's seriously going to affect the body's health. So in my mind, it's almost like doing laundry. If I throw some pants into the laundry or a shirt, am I going to do the laundry right away? No, I can wait for it to build up a little bit and then I do it. And I have the same thought with this kind of problem with the lysosomes. People are thinking about doing genetic engineering or adding cultured cells to bone marrow. I just don't see it as strictly necessary. And again, for that reason, it builds up so slowly. If we can get away with doing the injections, that would probably be best. And I had another idea. Well, we'll get into that a little bit later. Again, since these things build up so slowly, depending on how long it takes the lysosome to clear that stuff out, maybe it takes a long time and maybe it's not feasible. But even if it were to take a month or something like that, so you have to take a month-long therapy, it gets rid of all the junk. Now it's going to take another 20, 30, 40 years for it to build up to an appreciable level again. And my reasoning for not doing the gene splicing and things like this is the body is just not a good place for things over a long period of time. The nucleus, yes, it is a relatively safe place, but if we don't need to put it in there, I don't see any reason. Why take the risk is my question. If we can get away with just doing the injections, and if they work, and it clears it out in however long, a month, 2 months, a week, a day even, I have no idea how long it would take to degrade all this material. But we would only conceivably need to do it for a particular kind of indegradable material once every 20, 30, 40 years or something like that. So I see no reason to go ahead and do this gene therapy. It's just more complicated. This is something very simple, and why not keep it simple if you can? And getting into, again, the problem with the blood-brain barrier, and my idea, I don't know if this would be not good for any particular reason, but my idea would be basically to drill a small hole in the skull and create a port. And I know that this can be done. People who have bionic eyes, they have to drill holes in the back of their skull in order to hook it up to the brain. But of course you don't want a hole in your skull, because if something gets into it, then that's a serious problem. That's why there's so many protections against things getting into the passive blood-brain barrier. You have the skull and you have the blood-brain barrier. It's not good for anything to get in there. But since we're going to be doing it so infrequently, as I said, if it takes many, many years for this stuff to build up, we could do the injections for however long it takes to get rid of the stuff back down to basically zero, and then just seal it. That way we don't have to spend time trying to develop drugs to get past the blood-brain barriers. We just don't need to do it very often. Once every 20, 30 years is fine. The immune response as well. As I said, and as has been documented, the immune response has been very, very mild. And in some people, nothing at all. Again, this could be a problem if we're going to genetically modify cells or introduce some culture that is regularly putting this into the bloodstream. But for things related to aging, for someone with Gaucher's disease or something else like this, since they need it every day, really, they need it all the time. They have to get these injections every 2 weeks because this stuff builds up so quickly for them. But for aging, it takes so long. There's no need to have a constant supply. Again, do we need to do laundry every single time a shirt falls into the hamper? No, we can wait for it to build up a while and then do it. But again, even if there is a very serious immune reaction, we can use the drugs that we already have in place. They're very nasty drugs if you have to take them for your whole life. But if we only need to temporarily suppress the immune system, if we had to do it even, if the immune system is a strong enough response, we could suppress their immune system temporarily just for the course of the therapy. And then after they've already got rid of this junk, then we can cease the immune therapy. And we have already drugs like tacrolimus, mycophenolate, a whole host of other drugs that can do this. And it may not even, maybe even just with small doses of prednisone might be sufficient, or any other arthritic drugs or anything like that. These all suppress the immune system. So that's my thought, really. I hadn't really read anything like that. Those are just the thoughts I had years ago when I was reading up about this. So hopefully this gives you an idea of what is out there. Out of all of the things that are going to be treated for age-related problems, this is probably going to give people the least trouble, again, because it's already in clinics. All we really need to do is just find the right enzymes, which we already know are out there, and people have been finding them. Now, it takes a while to go into a random... First, it takes a while to find the bacteria that has it, and then to figure out which enzyme's actually doing it. It takes a while, but there are a whole load of new techniques now, molecular fingerprinting, things like this, where we're able to cut down that time. And of course, with computing power and different programs that people are writing, they're much better able to find this now. So hopefully this is able to give a good idea of where this is at today, and where people should look to in the future for different treatments that could possibly cure different age-related things in the heart, brain, any other organ in the body.